scientists have recently developed an exciting new framework called the Venus Life Equation that could change how we think about our search for life beyond Earth. This breakthrough was presented at the 2025 Lunar and Planetary Science Conference by Diana Gentry, director of the Aerobiology Laboratory at NASA's Ames Research Center, and it's got the scientific community buzzing. For decades, our search for extraterrestrial life has focused primarily on Mars and the icy moons of Jupiter and Saturn. But Venus, Earth's nearest planetary neighbor, has remained something of an overlooked sibling in this quest. Why? Because with surface temperatures hot enough to melt lead and crushing atmospheric pressure, Venus seems like the last place we'd find life. But what if we've been looking at Venus all wrong? What if there's a mathematical framework that could help us assess the real possibilities of life on this hellish world? In this video, we will explore this groundbreaking concept and discover why Venus might be more important to astrobiology than we ever imagined. The Venus Life Equation, VLE, provides scientists with a structured way to calculate the likelihood of life existing on Venus. Similar to the famous Drake equation, which estimates the number of communicative extraterrestrial civilizations in our galaxy, the VLE isn't meant to give us a definitive answer. Instead, it's a framework for organizing our thinking and guiding future research about possible life on Venus. The equation itself is elegantly simple. L equals O times R times C. In this formula, L represents the likelihood of life existing on Venus at any given time. The beauty of this equation lies in how it breaks down this complex question into three crucial parameters that scientists can actually investigate. O, origination, represents the probability that life arose on Venus in the first place. This parameter considers abiogenesis, life emerging independently, or panspermia, life arriving via meteorites from Earth. Research suggests Venus may have had habitable conditions for billions of years, similar to early Earth. R, robustness, measures the potential size and diversity of Venus's biosphere over time. This factor depends on available resources like essential nutrients, C, H, N, O, P, S elements, and energy sources. A more diverse biosphere is better equipped to survive when conditions change. C, continuity, accounts for the chance that conditions suitable for life have persisted from its origin until the present day. While Venus's surface became uninhabitable, its atmosphere might have provided a refuge. At 50 kilometers altitude, temperature and pressure conditions resemble Earth's, suggesting that microbial life could potentially survive there. By multiplying these three parameters together, scientists can calculate L, the likelihood of life on Venus. The VLE gives researchers a systematic way to approach the question and identify what we still need to learn. Venus and Earth are often called planetary twins due to their similar size, mass, and bulk composition. Both planets orbit within our Sun's habitable zone, though Venus sits at the inner edge. This fundamental similarity makes Venus's drastically different current state all the more puzzling and intriguing from an astrobiological perspective. Recent modeling studies suggest that Venus may have maintained habitable conditions for billions of years, possibly until as recently as 700 to 750 million years ago. During this time, Venus likely had liquid water oceans, moderate temperatures, and land-water interfaces, environments where life thrives on Earth. Plate tectonics, which plays a crucial role in maintaining a stable climate on Earth, may have also existed on Venus. However, Venus underwent a runaway greenhouse effect, transforming it into the hostile world we see today. Its thick carbon dioxide atmosphere traps heat so efficiently that surface temperatures reach a scorching 462 degrees Celsius (864 degrees Fahrenheit), and atmospheric pressure at the surface is 92 times that of Earth. Any liquid water long ago boiled away, accelerating the greenhouse effect. But while Venus's surface became uninhabitable, its cloud layers might still harbor life. At approximately 50 kilometers altitude, temperature and pressure conditions resemble Earth's, and this region contains water vapor and potential energy sources. On Earth, microbes have been found surviving at similar altitudes, and some researchers have pointed to unusual chemical signatures in Venus's clouds, including ammonia and unexplained UV absorption, as potential biosignatures. The VLE provides a structured way to evaluate this aerial biosphere hypothesis. The robustness parameter helps assess how viable such a cloud-based ecosystem could be. This also makes Venus a prime candidate for future missions searching for atmospheric biosignatures. The Venus life equation represents far more than just a tool for studying our nearest planetary neighbor. It has profound implications for our understanding of life in the universe and for how we approach the study of potentially habitable exoplanets. Earth and Venus present a natural experiment in planetary evolution. Despite starting with similar conditions, these twin worlds experienced radically different fates. Understanding why their paths diverged is crucial for interpreting data from Earth-sized exoplanets in the habitable zones of their stars. Current detection methods can tell us about a planet's size, mass, and orbit, but they provide limited information about surface conditions or atmospheric composition. As detection capabilities improve with instruments like the James Webb Space Telescope, frameworks like the VLE will help prioritize which planets deserve closer scrutiny. One particularly valuable aspect of the VLE is how it accounts for habitability changing over time. Many exoplanet studies focus on whether a planet is currently in its star's habitable zone, but the VLE reminds us that a planet's history matters. Venus might have been habitable for billions of years before becoming uninhabitable. This raises important questions. Are such transitions common? Could many exoplanets follow Venus's trajectory? The VLE also expands our concept of habitable environments. If life could persist in Venus's clouds despite hostile surface conditions, we might need to consider atmospheric biospheres on other worlds as well. This could redefine what we classify as potentially habitable planets. Upcoming Venus missions, particularly Da Vinci Plus and VERITAS, will provide new data to refine the parameters of the Venus life equation. Da Vinci Plus will send a probe into Venus's atmosphere, analyzing its composition, while VERITAS will map the planet's surface in high resolution. These missions could revolutionize our understanding of Venus's history and habitability, offering insights that extend to exoplanet studies. Thank you for watching this exploration of the Venus life equation. If you found this fascinating, please like, subscribe, and share your thoughts in the comments below. And remember to keep looking up. Some of our most profound answers might be hanging in the clouds of our nearest planetary neighbor.